All right, welcome. In this video, I want to continue taking a look at verification procedures for NP algorithms or problems that are in NP. Specifically, I want to continue focusing on NP complete problems, but we are just going to focus on the aspect of showing that they are in NP by stating and proving correct a verification procedure for them. So I do want to take a look at three problems, and again, I want to review each problem and make sure we understand the problem before trying to provide a verification procedure for it. And the problems that I want to look at in this video are all graph problems. And at least for these versions, I'm going to consider quite simply undirected graphs, though we could define version of these for directed graphs as well. And at least for the Hamiltonian cycle case, I will assume that the underlying graph is already connected. However, for clique and independent set, that's not something that I will require. However, also for both of these problems, the graph is not just the input. We will also include a integer k greater than 1. And then, well, let's look at the clique one in particular. The clique problem asks us to answer yes if there exists a clique. Well, the definition of a clique is a complete subgraph of size k or greater, technically. If you have a complete subgraph of size greater than k, that always includes inside it a complete subgraph of size k. Now, in case you don't remember the definition of a complete graph, a complete graph is one in which every edge that could exist does exist. Or another way of saying that is between any 2 points there exists an edge. So basically this term clique, also known as clique, is sort of related to the clique notion in social networks. A clique is a group of friends where they're very closely related or closely very tight, in the sense that every friend is a friend of everyone else, at least within that group, at least within that clique or clique. And so the clique problem as posed for graphs or networks in general is sort of just a generalization of that. For any network or any graph, can we find a collection of vertices that are all connected to one another? Every vertex has a connection to every other one. If we can, we call that a complete subgraph or a clique. And this problem asks us to see if we could find one of a certain size. Now, this is sort of a pure decision problem version. We could imagine a sort of a less decision problem version where in the yes case, we don't just want to answer yes, but we want you to tell us which subset of vertices it is that is that complete subgraph. And more commonly, we want to find the largest clique in the graph. Our second problem here, independent set, is a very similar problem to clique, and we can see that when we jump maybe into the output here, we can see that here we're looking for a subgraph of G of size k similar, but with no edges. It's sort of the opposite criteria here. A complete subgraph is one with all of the edges there. This is one with none of the edges there. And so this is what we would call an independent set in a graph. A clique is a complete subgraph. An independent set is a subgraph with no edges in it. And while finding a clique is, I sort of mentioned in a social network, a clique would be a group of people that all know each other or all friends with each other or some other relationship, whatever that edge represents. In an independent set, if we're talking about a social network, then these are all people that don't know each other or are not friends with each other, and the independence part might be important there. You might want to make a team of individuals that you want to make sure have no prior relation, and you might be looking for an independent set. The final problem is not really related to the first two, other than that it is also a graph problem. This one has to do with finding a Hamiltonian cycle. A Hamiltonian cycle is a cycle that visits every vertex in the graph exactly once, meaning we don't sort of loop back on any vertices. And of course, the Hamiltonian cycle is related to the traveling salesperson problem. If you're familiar with that, a traveling salesperson solution is a Hamiltonian cycle. But this asks the question of a given graph, can you even find a Hamiltonian cycle or not? Some graphs have them, some do not. Some graphs it's trivial to find a Hamiltonian cycle, others it is not. However, remember all these three problems, we're not going to consider trying to solve the problem, at least not in this video. We're going to consider trying to verify the problem that is given some extra piece of input, some extra hint. Can we determine if we should say yes or no? So we can start here with the Clique Verifier. And let's remember that our verifiers are going to take the same input as before. So we've got our same input as the main problem. So we've got G, but also our integer K. But our verifiers always take an extra piece of input as well. And that extra piece of input is going to be whatever we expect we're going to get from the prover. Now, remember, the prover can give us whatever they want, but it's our job in the verifier to make sure that if we're going to say yes, at least, that we're only doing that when they've convinced us that that is the right thing to do. So what would convince us that we have a clique of size k? Well, maybe, remember, what makes this problem hard in the general case is we have to try all possible cliques. Well, just tell us which clique it is. And so here I'm going to use a capital W. W again is one of my preferred names here for witness. But I'm going to use capital because I'm going to assume W is telling me the clique that is telling me which vertices it is that are in the clique. So I'm going to start out there. I'm going to say if W is not a subset of V, we'll say no. So after this step, we know that what the prover has given us is at least a subset of the vertices. Now, that's not enough. Any old subset won't do. We want a clique. So maybe the next thing that I'll try here, I'll say if it's not a clique. Now, how do I say if it's not a clique? I could say if W is not a clique, but that's vague. I want to be precise. I want to say, how do I test if it's a clique? So if it's a clique, remember that means every edge is there. So if there's a U and a V in W, so now I've got two vertices in W, such that now they're all supposed to have, all of our pairs of vertices are supposed to have an edge between them. So if we can find one that doesn't have one, so let's say such that UV is not in the edge set, doesn't have an edge, then we should say no. So if we've got this first test, we know that we've got a bunch of vertices. If we've got the second test, we know if we pass this one that all those vertices have an edge between them. So that means we've got ourselves a clique. So I sort of went in this order on purpose this time because we might at this point be a little bit sloppy and say, well, this looks right to me. Okay, close it off. Now I'm just going to say yes. And I might even go ahead and start trying my proof of correctness down here. But we're going to get stuck. We're going to get stuck in the no implies no case. We can say yes when we should say yes with this one, but we're not going to catch all the tricks. And the reason is we've forgotten one test. And how do we know if we've got all the tests? Well, I'm just going to move this down, make room for another test. How do we know if we've got all the tests? Well, we need to look back over at our problem statement over here, where we've got, it says, yes, if there's a complete subgraph of size k, all that we've done here, all this test has done, is the complete subgraph part, but not the size k. So we need to remember, oh, we forgot that part. If the size of W is, now remember, if it was greater than k, we're okay. But if the size of W is less than k, we should say no. Okay, and we'll see here in a bit why that's going to be, why that's key when we get to our proof where it's not going to work. So let's try our proof. Remember, yes implies yes here means if I should say yes, I do say yes. All right, so if we should say yes, what does that mean? Well, that means assume our input graph G has a complete subgraph of size k. which is taking the definition, the output criteria for yes here, and applying it directly. Okay, there exists a complete subgraph of size k. I'm saying assume there exists a complete subgraph of size k. Okay, now that we know that we have it, how do we continue our proof? Remember, we need to say that there's some w that's going to get us to the finish line, the yes. So we need to say which w it is. Well, this is the one we want. So let w be this subgraph. I need to be a bit more precise there. Let's say let w be the vertices in this subgraph. Okay, since w is a subset of v, it passes the first test, and since w is a complete subgraph, it passes the second test. Finally, since the size of w is equal to k, remember we assumed it was of size k, we pass the final test. And that completes that branch of the argument. So we're on to the second branch, the no implies no. And remember, I prefer the no implies no branch. I feel like it flows a little more natural, but if you want to do yes implies yes backwards, that's equivalent, that's the contrapositive. So in the no implies no case, we're going to assume that G has no complete subgraph. Again, usually that's just, if we've written this out in the right precise way, it's effectively changing an to a no here. And we want to continue now. Again, remember how I like to make this argument. So I'm going to assume we passed the first couple tests, and then argue that we didn't pass the last one. So we assume G has no complete graph of size k. So now we're going to assume W is a subset of vertices such that W is a complete subgraph. So we're going to assume both of these. W is a subset of vertices and it's a complete subgraph, so that means it passes the first two tests. But by our assumption, there is no complete subgraph of size k, so the size of W must be less than k, and we say no. Okay, that completes our proof. So now we only need to ask ourselves, is this indeed polynomial time? So let's double check. The subset check, I think we looked at that one last time. Worst case is going to be about an n squared. In this case, checking to make sure that all of our edges exist, well, that looks like it has something to do with the edge set. I'm going to say worst case that might be the size of the edge set, iterating through all of our edges. But it depends a little bit on how we're going to implement that. This looks like a constant time step. So indeed, this looks like altogether about a polynomial time. So as long as we're correct, which we've proven down here below, again, this is enough to show for us membership in the class NP for our problem Clique. Now, the thing again I want to show, and I think we saw this in the last video for a pair of problems, that clique and independent set are very closely related in fact, that we can make a very simple change. Now remember, here we were looking for, here in clique, let's go ahead and see if we can change this for a verifier for independent sets for a second. We'll still want us to tell us which vertices are the independent set, so we still want to subset the vertices. Now when we're looking for them, we're not looking to see if there's missing edges, we want all the edges to be missing. So in fact, we're just looking for any edge that actually does exist. If we can find any one that exists, we should say no, and if it's not of the right size, we should say no, but otherwise this verifier completely works. So all I did here was changing, taking it from looking for a missing edge to looking for an edge that exists there when it shouldn't. Okay. Now if we want to fix up the proof, there's probably a few places here where we say complete subgraph, where we probably want to say independent set, and so on. However, the argument, the language of the argument is going to flow almost exactly the same. Okay, if we swap out those key definitions. So independent set and clique very closely related. We showed directly that clique was an NP, but due to their close relationship, hopefully we can see that indeed independent set is also in NP. So I'll maybe finish here by making a second verifier here for Hamiltonian cycles. So I'll call this HC verifier. It's going to take our graph as input, but it doesn't take a k. So all that's left then is going to be taking our extra piece of input, whatever that might be. Now, in the last couple problems, we've been dealing with problems that had some sets involved, the subset problems, but also these graph problems are sets of vertices and sets of edges. And we've, in most of these problems at least, ended up with our prover giving us a subset. Now, notice that that's not going to help us here for Hamiltonian cycle. Hamiltonian cycle, we want to know if there's this tour that visits all the vertices and returns back where it started, or if no such tour could possibly exist. Now, telling us some subset's not going to help us there because our tour should include all the vertices, and that's sort of going to be critical here. So what should they tell us? Well, I think what is going to help us here then is we know that every tour includes every vertex, but we don't know what order we visit the vertices. Okay, and so since every possible ordering is at least one potential solution, there might not be an actual tour there, but it's one that we should check. That gives us n factorial possible orderings, possible tours we could have in a graph of size n. So what we're probably going to expect our witness to be, whatever we're getting from our prover here, is going to be a reordering of the vertices, telling us which order they should be in. So again, I'm going to start out there. Now remember, reordering, I guess, is a semi-technical term, but usually in math we're going to use the term permutation. So if W is not a permutation of V, say no. Okay, so after we get past this step, now we know that what the prover has given us is a permutation of the vertex set. So it's some order in which to visit the vertices. Now what we need to do is check to make sure that if we are trying to visit the vertices in that order, there's always an edge connecting any two. So I'm going to assume W is a sequence here of vertices. So I'm going to say if Wi and Wi plus 1, we want them to have an edge between them. So if they don't have an edge between them for any of the i's that we could have here, so it looks like our I is going to be in the range, we'll start at 1. So that would be the first one in our permutation to the second one to third one, and so on, all the way up to, but not including the last one, n. There is no n plus 1, so up to but not including. So if any of them is not an edge in this range, we'll say no. Okay, again, maybe we're inclined to say yes now, but let's make sure and double check. After this step, we know we've got all the vertices and no duplicates because the permutation is doing the heavy lifting there. That technical term is going to say make sure we're including all the vertices, but don't get any extra ones in there, no duplicates and so on. Just put them in a different order. Okay, so we've got them in a different order. Now what's this saying? It's saying I can get from vertex 1 to vertex 2, 2 to 3, 3 to 4, n minus 1 to n. Are we done? We might say yes, but we'll notice that this technically is the recipe for a Hamiltonian path, not a Hamiltonian cycle. We forgot the last step here, that if we need to double check that Wn connects back up to W1. So if that's not in the edge set, we should say no as well. Now I think we've been thorough enough that we can say yes, and we can end our verifier there. Again, quick check, checking to see if it's a permutation. That's like checking a subset too. We're just doing a membership checks here, so that should be about a theta n squared in the worst case. This looks like how many edges and one extra one here, so let's just lump them together and say that that's about order of the edge set. Same sort of scenario we got ourselves in earlier, definitely polynomial time. So all that matters is we need to make sure that we've got ourselves a correct verifier here. Okay, so to start, we want to start with the assumption that we should say yes. So the assumption that we should say yes means go look at our Hamiltonian cycle definition here. What does the output say? When should we say yes? It says, well, we should say yes if there exists a simple cycle in G that visits every vertex exactly once. Okay, the exactly once is a little redundant there, so I didn't leave that part in here, but assume G has a simple cycle that visits every vertex. Okay, That's what it means to have a Hamiltonian cycle. Now what? Well, we need a permutation. So I'm going to say assume W, we're going to assume that W is the order this simple cycle visits the vertices. That's the permutation that we were looking for. Now, since this ordering that we've got is a permutation of V, that was our first test, we're going to pass the first test. So next, now the next bit is we're going to rely on the fact that it is also a cycle. So since W is a cycle, since it's a cycle, we know that every edge in that cycle is going to exist. That's what we're testing for here. So we know in each of these edge tests that we're doing is going to come back true. So that's actually going to get us through 2 tests all at once. So we say yes. And that ends that branch. We're on to the next branch. Okay, so we get to finish. Let's try it off. And again, as I've mentioned in my previous proofs, I like to do the no implies no branch. So that means I'm going to again duplicate what I've got up here, but probably changing my to a no. Assume G has no simple cycle that visits every vertex. Okay, assume G has no simple cycle that visits every vertex, meaning now we need to set up by saying what are we going to do with our W up here. Now remember, I usually say let's try and get our W and assume it passes the first 2 tests, and then we'll worry about the third test. Hopefully the third test will not be true. So we'll say assume W is a permutation of V. That's got them in some reordering such that all of the edges in this range exist for the i's. Remember that we were interested in I less than or equal to 1, or 1 less than or equal to I less than n. Let's make that -1 since I put the equal sign in there by accident. So since we've got that in that range, we're going to assume that's true, but then that must mean that last edge does not exist. So since we know it has no simple cycle that visits every vertex, so the last edge must not exist, so we say no. And once again, we're done that branch. And by completing that branch, we complete the proof, okay, for Hamiltonian cycle. Now, there's another closely related problem called a Hamiltonian path. Hamiltonian path we could do. Only this last bit we wouldn't need in Hamiltonian path, so we've kind of already done it here. But that gives you sort of a model on how you could modify this proof or some of the other proofs that we've done earlier to try and prove and write verifiers for similar problems. Okay, I tackled a couple graph problems in this example. That's all I wanted to do in this video, so thanks a lot for watching, and we'll see you in the next video.